All right, since we didn't really get to power yesterday in class, I thought I would just do a short video of the basics about it, and I also have some examples. So power is related to work in that it's the rate at which work is done. So the idea is that we can think about how much work is done, but sometimes it's actually more useful for us to know, well, how quickly did it get done? And the quicker it gets done, that'll change the power. That would also affect, well, how much power did you use to get that work done? So it's a useful quantity. So we basically have two definitions of power. We have average power, which we're really following sort of the pattern we've had previously in terms of average and instantaneous quantities. So it's just the amount of work done over some change in time. That would be the average power. If we want to know the instantaneous power, it would be this ratio, but we're allowing the delta t to go to 0, so you might expect it's going to be dW dt, so the instantaneous power. So that would involve perhaps a derivative. The units that we use to measure power is called a watt. And so that might sound familiar because you've seen light bulbs are rated in terms of their wattage. When you get an energy bill, they talk about kilowatt hours, which actually you would see would be a unit of energy because it's a power times a time. You also might be more familiar with the British unit, or the units we use of power, which is horsepower. And here's a conversion. 1 horsepower is 746 watts. So here's an example of how the power could be different when we are doing the same amount of work. So let's say that we have to lift a box from one height up to a higher height. So, and let's say that took 100 joules of work to do. Now, the power that we would be expending would be different depending on the amount of time it took us. So let's say if it took us 5 seconds to do it, then we had to expend 20 watts of power. But if we do it in 1 second, which is much more quickly, that would take 100 watts of power. Example I always think of is if you have to climb the stairs, you're doing work because you're moving your mass up to a higher height, and that takes some work. But you know that you're going to be more tired if you run up the steps than if you just go up more steadily. And the key there is the amount of time it takes you to do that, and that means that you actually have to expend more power to go up more quickly. So here's a little example just so we get used to the idea of the units and how power is defined. So I have a light bulb, and I say that it's a 100-watt light bulb. And keep in mind that that's sort of the amount of work over time. If you remember the work energy theorem, we also remember we can think of work as measured in terms of energy because it's measured in joules. And so that might help us figure out how we would want to do this calculation. We're given the power, which is energy over time. We want to find energy. So it would it would figure that we would take the energy over the time and multiply by the time. This is going to give us the energy. So if we have 100 watts, that's our energy over time, and we want to multiply by the amount of time, well, we'd say 1 hour. But hopefully we understand that this isn't going to work unit-wise because a watt is a joule per second. So you just kind of put it in here, joules per second. And our units aren't going to work out. So we have to change hours into seconds. So we use some conversions. 1 hour is 60 minutes. And 1 minute is 60 seconds. Now we're going to be, this altogether is the number of seconds in 1 hour. And so if we look at our units, hours cancel out, minutes cancel out, and seconds cancel out, and our answer is going to be in joules. And it turns out that it ends up being 3.6 times 10 to the 5th joules, and that's how much energy we've expended. If we look at the definition of power, power is dW dt, and we keep in mind the definition of work that we looked at previously. The dot product of force and displacement. If our force is constant, when we take the derivative of this, we'd have dF dt dotted with s plus F dotted with ds dt, because that's how we do the derivative of a product. But this is 0 because we just said the force was constant, and so our power could be just written as F times ds dt, which is just the velocity. And so that's another way that we can write power as the force that's acting on the object times its velocity. So I'm going to do a final example for you. If we have an engine for an airplane, it has a power of 75 kilowatts when it's generating its full power, and then this engine allows a small single airplane of mass 730 kilograms to gain altitude at a rate of 2.4 meters per second. And the question is, what fraction of engine power is being used to make the airplane climb? So here I really think that this is, if we think of our little airplane, and it's flying along, there has to be, we're exerting a force upward that's going to have to be equal and opposite to its weight. So that's the force that we're going to apply, and the rate that it's climbing is the velocity. So here's an example where we're finding power as F dot V, which is just going to be FV in this case. So the force that we have to apply to make the plane go up has to be equal to its weight. So that's 730 kilograms times 9.8. And then the rate that it's gaining altitude is also its velocity upward. So that's 2.4. And when I multiply these together, I get 7.2 kilowatts. Now that's how much power is being used to make the airplane go up. Some of the power is being dissipated, working against air resistance, etc. So the fraction of the total power would be found as you take 17.2 kilowatts and divide by 75 kilowatts. This ends up to be 0.23 or 23%. All right, so that's just a little bit about power, not too much that we missed yesterday, and hopefully you find this helpful.